tail test, is the rejection region in the right tail or the left tail? Well, yeah, it's in the left tail, but we're forcing everything to go over the one. And so this we can't explain at our level here at the moment. Whereas if it were this way, actually, I guess what you could do is you could reverse these. But let's say for presentation purposes it was this. This would be a one-tailed test on the right. And so what would be the area of the rejection region? It would be all of 0.1, right? And if the area in the tail is 0.10, you can't use the table in the book because the table in the book is 0.05, it says. All right, so there are a few more constraints in this presentation, but I don't mind the way that it's presented in this case. And so if you have an F test in this class, or if there's an F test of variances on the homework, it's always going to be either the 0.05 or the 0.01 in the right tail. Okay? All right, so, just one other thing here. If we look at page 416 on, which we're not going to do in this class, but on page 416 it says ANOVA assumptions, and ANOVA just means analysis of variance. What you can do is you can test 3 or more variances all at once. For our purposes, we're only going to test 2. Sigma 1 squared versus sigma 2 squared. If you went on in statistics, you can compare 3, 4, 5, 6 variances, all in one test. But we're not going to do that here. That's for something later. So it's a pretty straightforward F test for analyzing variances. And like I said, for our class, all we're going to be looking at is equal to versus not equal to, and it's going to be presented in this method here. Good, that's it. Okay. All right, well, that's pretty straightforward. So that's it on the chapter 12, analysis of variance. And so then we go to the last part of this class, or this course, and it's chapter 13. And the title for chapter 13, I believe, is correlation and regression analysis. I think it's something like that. Is that what it says?
Yeah.
Okay. All right, and as I said, we're only going to do some of this chapter also. Just a portion of it. And we're going to spend most of the time explaining things graphically. And there's an example here in the book that I like. Let's see if I made use of it in my notes here. Yeah, I don't know if I did, but let's go over to chapter 13 here. And so it's called correlation and linear regressions. So let's see, what's the next chapter called? Yeah, multiple regressions. Okay, so we're only going to do simple linear regressions. And anytime anybody says linear, one should think lines. And so this regression analysis is going to deal with a line because it's a linear regression. Later on, if you go on in statistics, you can do multiple regressions. And multiple regressions don't necessarily have to be lines. They can be different types of relationships. And so in looking at the beginning of chapter 13, the first part says, what is correlation analysis? So there's a little definition down here. On page 463, it says a group of techniques to measure the relationship between two variables. Okay? And so what I'm going to do right now is I'm going to take page 464, chapter 13, and that graph right there. All I'm going to do is take that graph and put it on the board. All right? And so we're going to be dealing with this graph, which is in chart 13.1. And so it's going to be looking something like this. This is sales calls down here. and this is copies sold. So what they're going to be measuring is the relationship or the correlation between sales calls and copies sold. And so for our purposes here, these are two variables. Sales calls, copies sold. And what you have down here on this axis is what we call the independent variable. So this is the independent variable down here. And what we have over here is the dependent variable. And so, if I were to ask you, which depends on which? Does copies sold depend upon sales calls, or do sales calls depend upon copies sold? And most people say, copies sold depend upon sales calls. That's how you make a copy sold, by making a sales call. And so, as I've said here, the independent variable goes down here, the dependent variable goes up on this axis right here. And so all I'm going to do now is just plot the data that they had here. So they go from 0 to 50, so this is 0, 10, 20, 30, 40, 50. So if you make 50 sales calls, let's see how many copies are sold. And that goes from 0 to 80. So we'll have 10, 20, 30, 40, 50, 60, 70, 80. So here's 10, 20, 30, 40, 50, 60, 70, 80. And so all they're going to do now is plot some data. So what happened is that somebody made 10 sales calls and got 30 copies sold. So all I'm going to do is just plot this data right here. And then somebody made 10, sold 40. Then there were 20 calls for 30. Then it looks like 22 calls or something for 30. Then there was a 40 and 22 calls. And then there was 50 on 20 calls. Then somebody made 30 calls and sold 60, so that's like right about here. Somebody made 30 calls and sold 70, and then another person had 40 calls and sold 60. So all we've done here is just plot the 2, 5, 7, 9, 10 points. There's 10 points of data that are plotted on this graph. Everybody see that? Okay. So if one were to look at this data, what's the correlation between sales calls and copies sold? Is it negative? Is it positive? Is there no correlation?
Positive.
It seems as though it's positive, meaning the more sales calls, the more copies sold. And so what we're finding here is that, okay, we can determine the correlation between sales calls and copies sold through linear regressions. All right? And so if you look at page 465, it talks about the correlation factor, and it shows you an R. Now, R is the correlation coefficient, right? And so if R, and you don't really have to know how to determine R, because what happens is that in most of the software packages that we have, you put the data in, and out comes the correlation coefficient, and out comes the coefficient of determination. Out comes R and R squared, which we're going to get to in a minute. And so the reason why I'm presenting it this way graphically, because I think it's easily understood this way. And even though you don't have to know how to calculate R and R squared, all I'm trying to do here is to explain it so that when you go out there in the world after this course, when somebody says, oh, we did some multiple regressions or some linear regressions, and they say R squared is this, you'll have an idea what R squared means. or if R is this, you'll know what R means. You'll know what a regression is, basically, graphically, because that's pretty much all you have to know in order to be able to understand what's been done. You don't have to know how everything's calculated, you just have to know some of the basics of regressions. And so that's all we're trying to do here, is give you some of the basics of regressions. And what a regression is it's just a bunch of data. And since it's a linear regression, what they're going to do is we're going to put a line through this data. One line through the data. And if you look at the correlation coefficient here on page 465, you see that perfect positive correlation is a perfect line where all the data is on the line. Perfect negative correlation is also all the data is on the line, but it's a downward sloping line versus the perfect positive correlation, which is an upward slope of the line. And then they give you some ranges down below. Perfect negative correlation is a -1, perfect positive correlation is a +1, meaning R. Okay, an R of -0.97. That's almost like perfect negative correlation. Okay? And there's the correlation coefficient. That's on page 468. That's how you calculate it. But for our purposes, we're not going to learn how to calculate it. All you know is that R is the correlation coefficient. And if it's a -0.7, that means it's negative. Not perfect, but significant. If it's 0, R is 0, there's no correlation. If R is 0.89, that's significant positive correlation, okay? So just remember that. And all we're going to do for the last thing is to jump over to page 476. And it's regression analysis. And so this line is the regression equation. Let me see where it is. And this is it. Everybody know the designation of a line? Y equals mx plus b. Everybody remember that from someplace? I don't know if it was geometry or whatever it was, but y equals mx plus b. What we've done here is all we've done here is we've gone b plus mx. What's b? Intercept. And this is the slope. And what they've said here is that they've said in this equation, this line is 18.94 plus 1.18 42x. And so now the question is, well, okay, here's the regression equation. Well, why is that the regression equation? And so what happens is you go back to this, and this equation is the estimate. But as you can see, the estimate has some error. Because what are the actual data points? If you if you made 10 sales calls, it says here that your estimate should be 35 copies sold. But what actually happened? Well, one person had 30, the other person had 40. And so that's called the error between the actual and the estimate. So each one of these data points has an error factor to it. And if you sum up all of those differences, actually, they're going to be squared differences. If you sum all of the squared differences up, you get a minimum relative to any other line that you would run through this data. And if you have a minimum squared difference or a minimum error, that's the best estimate. It might be terrible, but it's the best. Meaning that this line is better than this line. And why is that solid line better than the hyphenated line? Is because when you take the difference between all of the actuals and the estimates, they sum up greater than the solid line. Okay, this one might not be, you know, this observation right here has a smaller error if you use the dotted line, but this one over here has a lot bigger error factor, and so when you sum all the squared differences up, this dotted line would have a bigger, larger error. And so in statistics, we try to find what they call the best fitting line. And the best fitting line is the line that has the least error. And if the line has the least error, then it's called the best estimate. And so what the book says here is, it says, based on this data right here, that's the best fitting line. This one right here, 18.94 plus 1.1842x, better than 17 plus 2.24x, or any other equation for a line. This is the best fitting one. Best fitting lines mean best estimates. And as I said, it might be the worst estimate. It might be a terrible estimate, but it's the best one. And that's what we try to do in statistics. We try to make the best estimate, given the data that's presented to us. And so, if you were to look at this right here and say, okay, yes, that's the best fitting line because it equates to the minimum error, then what would your relationship be, or what would your estimate be if you made 33 calls? 33 calls made. What's expected copies sold? Okay, well, if you look at this graphically, 33, you would say, well, here's 33. Looks like it's, well, I don't know how about my graphs doing, but it looks like it's a little bit over 60. Graphically, not a very good way to present it. Put it into the formula for the line, you'll know exactly how many copies are estimated to be sold. So what we would do is we would say, why? Now, because this, remember, this axis over here is the y-axis. It's the dependent variable. This is the x-axis down here. So what we're going to do is we're going to estimate y because it's dependent upon x. And so this would be y is equal to 18.94 plus 1.1842 times 33. And so what would it be? Y, which is copies sold, is equal to how much? How many copies sold if you have 33 telephone calls?
58.
Is it 58?
Yeah.
Ah, too bad. So I'm just gonna say this goes down a little bit below the 60. So it's 58, you said 58 what?
Yep, 0.01.
58 point, yeah, just say 58. I'll say 58.01. Yeah. So if x equals 33, then y is equal to 58. Based on what? The regression. What's the regression? You take data, you fit the best line. The best fitting line has the least error or the least deviation between the data and the estimate. And so this is our estimate for copies sold based on the number of telephone calls. And so you can use this for planning purposes, you can use this for whatever purpose you want. And so, as we looked at R, what was R? R was the correlation coefficient, the relationship or the correlation between sales calls and copies sold. In regressions, another statistics that's thrown out is R squared. And what's R squared? Coefficient of determination. Let's see where that is. There it is on page 487. And what is the coefficient of determination? It says the proportion of the total variation in the dependent variable y that is explained or accounted for by the variation in the independent variable x. So if you can get something like r squared is equal to 0.94, that means that that equation is explaining 94% of the variation in the dependent variable by the independent variable, meaning that you've explained a lot of the estimate. Not all of it. So the object, when you do regressions, is to get R squared as high as you can go. You love to explain 100%, but we barely never do. So you try to get R squared as high as you can, and there's different ways to go about that. For our purposes right here, all we're saying is that there's data. We plot a linear regression against this data, and we come up with the regression line. And regression lines have R squareds. Coefficient of determination, and we just leave it at that. We don't get in this course into how to improve R squared or whatever. So as it relates to regressions, I think this is a simple way to explain it graphically. Relationship between data, estimate, which is the equation related to a line, show how if you vary x, y changes. And the coefficient of determination tells you how nice of a fit we have here between y and x. How much of y are we determining with this equation? Okay? Everybody understand simple linear regression? Okay? Yep. All right. So that's all I wanted to do today. I wanted to do two things. I wanted to do analysis of variance, because we've done so many hypothesis tests before, very similar, same 6 steps, just a different distribution. And the distribution is a skew distribution. It's an F distribution, so therefore it has an F-test statistic. Remember that when you run through your hypothesis test of variances, when you calculate the F-test statistic, the higher variance goes in the numerator, the lower variance goes in the denominator, and based upon which one's in the numerator and which one's in the denominator dictates how many degrees of freedom you have. Don't forget that. Degrees of freedom may be higher in the denominator. Okay? So whatever is in the numerator, don't forget the degrees of freedom go along with the sample size of that variance. Sample variance. Decision rule is a 1 or a 2-tailed test. You know how to calculate the critical value from the table. And so now you know how to test variances. You test variances so that you can use the appropriate T in the test statistic when we're comparing and analyzing unrelated population means. And then we jump into a little bit on regression analysis, correlation, and it shows here that you have a set of data between two variables. One's a dependent variable, one's an independent variable. The independent variable is always on the x-axis. The dependent variable is always on the y-axis. You just plot data, and when you plot the data, you can run a line through it. And the line that's the best line is the line that has the minimum distance between the estimate, which is the regression line, and the actual data. And when you sum up all those errors, it's a minimum. And because it's a minimum, that's the best line. And because it's the best line, that's the best regression equation because it minimizes the error. And so you just have to come up with the line. And you on your way to determining the relationship between the independent variable and the dependent variable. And as I said, on Excel or whatever it is, the software package you use, you put in data, you tell it to run regression, it'll come out with the line. It'll come up with R squared, it'll come up with R. And all you have to do now is be able to interpret what it's telling you. Okay, so when you plug the data in and out, and it spits out this equation right here. Based on this data, it spits out this equation. And it spits out an R squared of, let's say, 0.94. I don't even know, maybe they did R squared here. I don't even know if they've done it, but
Page 49.
maybe they did. Page 489, see page 489? Coefficient of determination, that's how you calculate it. It takes you like 4 hours to calculate it manually.
Oh my gosh.
Okay, when I went to school, when I had statistics, there were no calculators, so we had to do it manually. Man, this is an equation that takes a long time. So be thankful that you're learning later than I did. And so, like I said, I don't know. I bet it's in here someplace, but I can't seem to locate it that quickly as to what R squared is based on that data right there. I thought I could find it on page 493, but I don't think it's there. But whatever it is, when you see an R squared at 0.94, that means the data line is determining 94% of the total variation between the two, y and x. Okay, which is pretty nice to know that you almost have the whole thing in that one little equation. Okay. Anybody have any questions on analysis of variance? Testing variances, two variances, and this graphical explanation of simple linear regressions. Oh, anybody has any questions? Okay, so that's it.